AP Stats, this is Unit 10, chi-square inference. This is going to be the fifth and final section, well, final new section, or section that covers new material for this particular unit, Unit 10. So this is 10.5. There is a 10.6, but 10.5 is the last one that goes over new content. So in the next handout, it's going to be mostly just review. So we're going to be concentrating on being able to identify which appropriate test to use for each of these for problems. I'll give you a bunch of problem stems, which is the correct test that we should be using in either of those situations. So that should be a quick video. This one's going to run just like any full lesson, but the other one should be pretty quick. So we're moving into the last test, tests for independence or association. They happen to be the same type of test, just different names for them. And that's because if variables are independent of each other, they're not associated. If variables are associated, they're not independent of each other. So they have two common names, and that's the reason why. So variables that are not associated happen to be independent of each other. So that's just a statistical definition, or that's the relationship between two statistical terms. So the way that we checked for independence beforehand, and this was back in Unit 4 when we went over basic probability. So there were portions, I think there was the topic where we talked about, what was it, intersections and the multiplication law, and also conditional probability, because conditional probability shows up in the general multiplication law. We talked about independence between variables, and that had to get expressed using conditional probabilities. So conditional probabilities, if they just boil down to simple probabilities, then we would say that those two events that are inside of those formulas are going to be independent of each other. So that's what this is what they ended up looking like. So we have two events, A and B. I don't know why I put subscript zeros on them. So A naught and B naught. No idea. But if we have two events, A and B, oh, that's the reason why. So we have two variables, A and B, and these are both categorical variables. A naught and B naught happen to be specific constant values for A and B. So that's a specific category within A and a specific category within B, B naught. So we say that event A naught, because you can think of those as two individual events. An event being that this particular person or this object or individual happens to be in this particular category for that with respect to that one variable. So probability, they're in category A naught, given that they're in category B naught, is equal to the probability that they are in category A naught. So that's a simple probability. So if, basically what this is saying is if the probability that they're going to be found in a particular category, already knowing that they're in this category with respect to this other variable, if that just drops down to the rate at which all individuals are in that particular category, then we say that these two variables are independent of each other. Actually works both ways. If you switch the order, and that's also true, then that's the complete version of this. So then we would say that these variables are not associated or are independent of each other. So simply put, knowing that the first event happens, actually no, knowing that the second event happens, probability of this event occurring should just equal to the probability that occurring, not caring whether B has happened or that second event has happened. So if those conditional probabilities just drop down to simple probabilities, these two variables are independent of each other. So this is actually part of the mathematics behind the calculation procedure for expected counts for the test that we just saw earlier, the homogeneity one. So basically what this means is that the proportion of one group of people in this group of people, if that just drops out to the proportion of this group of people out of the whole. Right, so in this case, we're talking about tables. So if we're looking at one category, if the proportion of people being in one category out of this category is the same as the proportion of this category, or not this category, I think it's this category out of the whole, wherever the whole is at, which they didn't give the whole here. So that's just the same thing as the table rate. So if a conditional rate is the same as the corresponding table rate, in other words, these distributions are proportionate, then we say that the variables are independent of each other. And that's actually the reasoning behind the calculation procedure. What we do is we assume that there's no difference between these variables or no association between these variables, and we take a row total and a column total, and we multiply those and divide them out of the big total, the actual total. And basically what we're doing is we're taking a rate out of the whole and multiplying that with the amount out of the whole for the other variable. So it has that in play there. So we'll go ahead and go straight into it. So how to actually run these tests, how to set them up, and how to run them. And what's the difference between these and the homogeneous situation or the homogeneity situation. So we'll look at number one. Table below is constructed using data from the article Influence of Socioeconomic Status on Mortality After Stroke. So this was an actual article in a medical journal called Stroke, 2005, 310 through 314. That's the pages that in the article or that's the pages the article was found inside of that journal. So one of the questions of interest was whether there was an association between survival after a stroke and the level of education. Medical records for a random sample of 2,333 residents of Vienna, Austria. So I'm probably going to write that down. That's more than likely the table total. So these are residents of Vienna, Austria. So it's a random sample of 2,333 residents who had suffered a stroke. We're used to classify each individual according to two variables. This is observational data, by the way. So these are based off of maybe medical records. Survival is one of the variables, and there's only two categories, whether they survived or they ended up dying. And then level of education is the other variable, and there are 5 different categories. No basic education is the first. Secondary school graduation, so they graduated their secondary school, which is like high school. Technical training, higher secondary school degree, maybe like what we have in the States, which is an associate's degree, and that's distinguished from a university graduate. So like a bachelor's degree, of course in Austria they probably have a different system, education over there. So for letter A, researchers wish to test whether or not there is an association between level of education and survival of stroke victims. State an appropriate set of hypotheses, so we want hypotheses. So they're trying to figure out, is there a relationship between survival of a stroke and what your level of education was? So does your level of education, does that have anything to do with whether or not you'll survive your next stroke or whatever? So how do we check the table for that? The mathematics ends up being the exact same for a test for homogeneity. Instead of thinking of these as individual populations of people, statistically that's not what's going on. These aren't individual samples of types of people. This is one sample of people. It's one big group of people, and we're just splitting those people up with respect to 2 different variables. So it's 2-dimensional data because we're tracking 2 pieces of information per individual. How many individuals? 2333. So then we think of them in terms of 2 different variables. And in the first variable, we'll talk about survival status. So what we'd like to do is probably come up with the entire totals, which I'll get those later, because here we just need the hypotheses. And hypothesis, or a null hypothesis, will be the first one. We just need a statement. And the statement would be, are these variables related to each other? For the null, we assume there's no relationship between the 2. So no relationship whatsoever. These variables are independent of each other. So the easiest way to say it, in my opinion, there is no association So that's the way that I prefer to go. There is no association between, and then you name both variables, and then you name the population that this is applied to. So there is no association between. And what are they? Survival of stroke, simply put, and level of education, or education level if you want to go ahead and get rid of that third word. Level of education. And that's 4. So I got to be careful. The group of people that they sampled were residents of Vienna, Austria. So if this is a representative sample, the largest group of people that it represents would be all residents of Vienna, Austria. So for all, at this point when I'm writing a hypothesis, I don't care whether or not this is a representative sample. All I'm trying to figure out what's the maximum population that this could be generalized to, assuming this is representative. So the maximum group of people that we can generalize this to would be all residents of Vienna, Austria. All Vienna, Austria residents. Then I ran out of space. Well, not really. Okay, so that's the null hypothesis. Several things here. The null, no association. They are independent. So another way that we could have written this is that these two variables for all Vienna, Austria residents are independent. So these two variables are independent. So that one I personally don't like the way it flows. I'd rather say there is no association between variable 1, variable 2 for population, whatever it is. Alternative, very simple. There is an association, and that's it. So there is an association. And then I'll put an ellipsis. That keeps on going. And that should be good enough, especially if this were an AP exam, you'd be fine with this. So then now I have to calculate expected counts, and for that I'm going to need the table totals. Let me go ahead and calculate those, and then we'll be back once I got those. And there they are. So those are my row totals and column totals. Expected counts, this procedure for calculating the expected counts is identical to the procedure for calculating the expected counts in a homogeneity situation. So the exact same procedure. And do we remember what that procedure was? The formula, the expected count, is equal to the row total times the column total divided by the sample size in this case, which we can call it n. So the formula is a lot nicer to express here for this situation. The key distinction between this has to do with the key distinction between a test for association and a test for homogeneity. So in a homogeneity situation, multiple samples, it's only one variable. So it's one variable versus multiple samples, and that makes two-dimensional data because it's a single variable with all its categories, but for multiple populations. In this case, we have one sample, one population, two variables. So there is no mathematical difference between those two situations because both of those just boil down to a matrix, a two-dimensional matrix. So mathematically identical. Statistically different because statistically there's a difference in procedure for obtaining this data. So in one situation there's a single sample. In the other situation there's multiple samples depending on how many populations you're doing this for. One variable. So I'm going to repeat this again for the review section for the next video. So the key distinction between homogeneity and association. Homogeneity, multiple samples, one variable. So one variable, multiple samples. For association or independence, it's one sample, one population, two variables. So two variables, one population. It's just the number of categories per variable is going to vary. So in this case, it's an easy formula to write. N by itself is just the sample size. So I couldn't have used N for the previous topic because it was a total, which was you take the sum of all the N values, of all the individual sample sizes. In this case, it's just a single sample size. So row total times column total divided by N, which is the sample size. So I'm going to go ahead and make a table for all of those expected values. This should be a 2 by 5, 2 rows, 5 columns. See if I can do this okay. So 1, 2, 3, 4, 5. That don't look too bad. Then I'll go ahead and fill these in. I'll go ahead and fill in the first one. So for the very, very first one, where the 13 is at, no basic education, and they passed away from that stroke. So the 110, you're going to multiply the 110 with the 369 and divide that by the sample size, 2333. So for this first one, this is 110 times 369 divided by 2333. And that, if I plug that into my calculator, 110 times 369, and that's divided by 2333. 17.3982, which if I round that to the nearest hundredth, 4 significant digits, 40. Then I'll go ahead and do this with every other one, and I'll just come back once those are all done. And here are the expected counts. So those are all 10 expected counts. Letter C. Calculate an appropriate statistic to measure the association of these two variables. And we'll go ahead and do that. It's going to end up being a chi-square value anyway, if the conditions are met. So I get to write chi-square instead of maybe some other letter if these expected counts are big. And if you look at that, all of those are bigger than, well, what's the minimum expected value for something that does satisfy the conditions for using a chi-square value? And it should be 5. So all of these should all be 5 or bigger. And the smallest one I see is 17.4. So I get to use the chi-square symbol. This is going to equal 2. And remember, it's a summation. It's a double sum. It's a two-dimensional sum because we're not only summing against all rows, we're summing also against all columns. But we'll just write a single sum symbol. O minus E, quantity squared, divided by E. And this will equal 2. We'll start off with the first, 17.4 minus, so that's the observed, actually that's the expected, not the observed. Observed was 13, I'll move that over here. 13 is the one that's circled still. Minus expected, 17.4, square this, divided by the expected, 17.4, plus an ellipsis, plus the last one. So you only have to draw the first and last, or write the first and the last one. So for the very, very last one, we're talking about staying in first row, and then exhausting all the columns, moving down to the second row afterwards, and then exhausting all of the columns, and the very, very final entry would be 279, which was observed. So 279 minus the expected in that category, 256.18 squared. This is divided by 256.18 because that's the expected. And this should equal to, well, I'm going to go to a calculator for this. So if you remember from last time, it's going to be the same procedure as the one for homogeneity. We are going to have to save the contingency table data in the form of a matrix. So we'll start that up by pressing menu in a calculator page, obviously. So we won't need the list in spreadsheets page. List in spreadsheets is good for forming one-dimensional arrays, which is a single variable data set, and then naming each of those columns. And each of those columns refers to one variable. I couldn't section 2 of those or more to say that that's one matrix. So you'd want to go the route of going to the calculator and opening up a matrix creation menu. So that's done by menu 7, 1, and 1, I think. Or was it? I just want to double check. Menu 7, 1, and yeah, 1. So this has 2 rows, 5 columns. So it's a 2 by 5. Press OK. And we'll go ahead and input the data. 13, 91, 196, 33, and 36 for the first row. Second row, 97, 397, 959, 232, 279. Let me just double check that I typed those in properly. It looks like I did. Yeah. Okay, next, before I press enter, you want to store this. There's a store function, control variable, and we can name it whatever we want. I could say OBS for observed. Earlier we were just using the letter O because we were being lazy. So O is good enough. Menu. We want statistics number 6, stat tests number 7, number 8 for two-way tests. So there are two chi-square functions. First one's for goodness of fit, and that's obviously what you're going to use for goodness of fit. And then this one 2 ways for both homogeneity and association. Mathematically equivalent. So this was matrix O. So what is it that we wanted from this? We've already gotten the expected values, and I did those by hand, which was a bad idea. Completely forgot that I could have gotten those by the expected matrix thing. So there's that. So hopefully you didn't do them by hand. Hopefully you remembered. I didn't, but hopefully you remembered how to find the expected matrix. So you would use this function after having already stored as a matrix the data that we were given. And what we're wanting is the chi-square statistic. I'm going to go ahead and steal the degrees of freedom too, which degrees of freedom is easy to calculate. So in this case, we have chi-square is equal to 12.2186, and we'll copy that down onto our handout. So the chi-square value that the calculator gave us was 12.2186. Degrees of freedom was 4, and we'll show where we got that from. Now degrees of freedom, same formula as the one for homogeneity. Number of rows, minus 1. Number of columns, minus 1. You multiply both of those. So in this case, there are 2 rows. So it's 2 minus 1. There are 5 columns, 5 minus 1. So that ends up being 1 times 4, 4. That's easy to verify. Now I've seen it on AP exams where they don't actually ask you to run a full test. They combine multiple concepts. So maybe they'll give you data like this, and one thing that they'll ask you to do is to give an appropriate graph for showing how these two variables are related. In other words, how the level of education is distributed across each survival categories. So in that case, you'd probably do like a segmented bar graph or a side-by-side bar graph. So that would be one part of the problem. Then they'll ask you to calculate a probability based off of the table, most likely like a conditional probability. And then they might ask you to not to run a test, but to maybe calculate an expected count, or maybe to calculate the degrees of freedom by hand. So that's something you'll have to know how to do by hand. But anyway, letter D. So we're just concentrating on the test procedure itself. So sometimes they don't give a full procedure, sometimes they do. So you want to be able to make sure that you know the ins and outs either way. So for letter D, assuming all conditions for using an appropriate chi-square test are satisfied, so in other words, the conditions for using a test, there's only 2 of them, random sample condition and then the large expected counts condition. So, and I think both of those are satisfied, but they didn't ask us to check. Those are easy to check though. Is there significant evidence to conclude that these variables are associated? And for that I need a p-value. The p-value that the calculator gave us was, let me look back at that, 0.0158. They didn't give us an alpha level. They didn't assign one, I don't believe. So we'll go ahead and use our own. So in this case, I'm going to use the one that we normally use in class. I'm going to say it's less than alpha equals to 0.05 because I'm already using, in my head I was already going to use 0.05. That's the default. And this is less than, so that's smaller than, that's 1.6%, smaller than 5%. So because that's the case, we say that it's a small p-value. So I'm going to go ahead and argue because the p-value is small, so I'm just saying that the p-value is small, but I've already demonstrated what we mean by that the p-value is small. Because it's less than that alpha level, we reject. So when the p-value is low, we reject the null hypothesis. And then we go ahead and conclude or give a conclusion statement in context. So we explain what that means in context. There is enough evidence to conclude, and we'll go ahead and check. We rejected the null. Null was that there was no association. So that means we're going to go ahead and conclude the other, so the alternative. There is an association. So there's enough evidence for us to go with that instead of the first. So there is enough evidence to conclude that there is an association between survival of stroke and education level. In Vienna, Austria residents. And that's it for this particular test. So that one they guided us through the steps, 4 different steps, A through D. So we're probably just going to go through another one of these without the guidance of those types of steps, and then we'll be done with this particular handout. Fix that. So I think I moved something accidentally. Yeah, there we go. Okay. So then, of course, every time I introduce a new procedure, I'll give a breakdown of it or an outline of what to write down. So it's basically like a template for running a full step or a full 4-step procedure. So step 1, hypotheses. So there is no association is the null hypothesis. categorical variable number 1, categorical variable number 2, for whatever the population is. So basically what I wrote down earlier, I follow that template all the time. Step 2, identify the procedure that you're supposed to be using. So chi-square test for independence or for association. Doesn't matter which word you use. And then there's 2 conditions. Random sample, so 1 random sample. Make sure you notice that. For homogeneity, it's however many samples you have, and they have to be independent of each other. So if it were 3 populations that you are comparing, there needs to be 3 independent random samples. In this case, a single random sample is given for independence or association. Then all expected counts need to be large, and large, what's good enough? 5 or more in every category or every entry. So then step 3, you calculate your chi-square statistic, which is just the same formula. Degrees of freedom, formula is given here, and then your conclusion for step 4. So we'll try this for number 2, and we'll be done. For for problem number 2, and this reads, the paper, Facial Expression of Pain in Elderly Adults with Dementia, Journal of Undergraduate Research, 2006. If I remember correctly, this paper concluded that patients with dementia don't always give accurate ratings of the pain that they're actually feeling, but that the facial expression that they had was more in line with what was going on with them. So the idea was we shouldn't be going by, or doctors shouldn't be going by just what they're reporting on paper. If you ask them what level of pain they're experiencing, those answers might not always be accurate. So sometimes looking at their facial expressions was a better way to judge what's going on and to see if they can come up with what's it called, giving appropriate care, stuff like that. So this paper, and I'll continue reading, examined the relationship between a nurse's assessment of a patient's facial expression and the patient's self-reported level of pain. Data for 89 randomly selected patients are summarized in the table below. Because patients with dementia do not always give a verbal indication that they are in pain, the authors of the paper were interested in determining if there's an association between a facial expression that reflects pain and self-reported pain. Is there enough evidence to conclude this based on the sample data? So here's our sample data given in the form of a table. We have one group of patients, 89 of them. This is one random sample of 89 of them. So that'll be the table total. And I think these are easy numbers, easy enough at least for me to try to make totals of them. This is obviously 20. This one is what, 69? 20 plus 69 is 89, so that works. 17 and 40, 57. 3 and 29, 32. And then those should add up to 89 as well. So that was pretty quick and easy. So is there enough evidence to conclude this based on the sample data? So when they ask you, is there enough evidence? And they're going to do that on the AP exam free response section. So in this case, it's only a free response test. So I'm pretty sure that we're going to be guaranteed one of those questions is going to be A, and that's what sucks too. If you remember everything I've been saying throughout the year, there are 6 problems. Problem 6 is a very, very large problem, twice as big as the other 5. You're usually guaranteed 2 inference procedures out of those other 5. Or sometimes it's found in part in problem 6. So you're guaranteed 2 occurrences of a statistical test. Now, because we have only 2 problems, 2 free response problems, I'm guessing you're to expect 1 inference procedure. So that's going to make it really tough because you're going to have to study so many of these different types of procedures, and you're probably only going to get 1 on that particular test. Maybe they'll find some way to incorporate inference in both problems. Maybe not, and in which case it's even much more recommended that you study the stuff quite a bit. So the safe route is to expect at least 1. How many there are going to be, who knows? Now, what's the indicator that they're looking for you to conduct in inference procedures? This is the most important thing. So what is it that clues you in on the idea that we're supposed to run an inference procedure? Is there enough evidence to conclude something? So is there enough evidence based off of data? They want you to run an inference procedure. So many times when I've graded mock exams, so by the time that they get to the free response section, they've already been completely destroyed by the multiple choice section. That multiple choice section is a tough one, which again, you guys are lucky you're not going to have to go through a multiple choice section. They're already super tired after having taken the multiple choice section. By the time they look at one of these problems and this type of a problem shows up, you're super tired, and either you're completely oblivious to the idea that they're looking for an inference procedure, like a statistical test or a confidence interval, and you write some like BS paragraph arguing based off of something else. Or you just look at the data and you make some shallow statistical arguments, or you look at a graph, or you give a graph and you make some shallow statistical arguments there to argue for evidence for whatever claim that they're making. No. When they ask, is there enough evidence to conclude something? You're going to do a test. So it's some sort of statistical test. In this case, it's a chi-square test. So eventually, chi-square test for, and hopefully it's not a big shocker, this is a test for association. Now, on test day, you'll have to figure out what type of test. It's easy in one of these handouts because we're concentrating on a specific procedure on this particular handout. So eventually I'll go ahead and write that, and then we're going to have two conditions for this. What I'm missing first off, because I skipped from step 1 all the way to step 2, step number 1, hypotheses. So in this case, since it's a test for an association, there is no association between self-reported level of pain and their facial expression expressing pain. So I might want to use their wording. Is there an association between, and I'm reading this second to the last sentence, facial expression that reflects pain and self-reported pain? So the way I was describing it earlier is a little bit different compared to the way that they're setting up the test. So is there an association between self-reported pain and a facial expression that reflects pain? So whether or not their facial expression reflects pain and what they reported by themselves. So there is, in this case, no association for a null hypothesis. That's something you'll have to memorize. No association between facial expression reflecting pain and self-reported pain. So the idea here is if they're not reporting pain, so will it show up in their facial expression? Will it look like they are not in pain? Or if they are reporting pain, will it show in their facial expression that they're feeling pain? So that sort of thing. Or could those be completely independent of each other? Which in this case, that's the alternative. There is no association between. So there is no association between. And then I'll just go ahead and leave it at that. That's good enough. So those are my hypotheses. Now back to the conditions. So conditions, random sample is given, I think, 89 randomly selected patients. So random sample given. It's a single sample, so I don't have to check for independence between samples. This is good enough. The second condition, is this sample large enough? And the samples large enough will manifest itself in large expected counts. So do we have large expected counts? I don't know what the expected counts are. You might be tempted to look at that 3 and say, well, no, this doesn't look big enough. But it's based off of the expected counts. What was that expected to be? Now we could do this by hand really quickly, or we can just go ahead and steal that information from the calculator, which I'm going to go ahead and do. So here, I'll go ahead and just copy down. So I went ahead and did this on the calculator. I'm not going to end up showing it. So it should be pretty simple plugging this into the calculator. So just for the sake of making this video as short as possible, I won't show the calculator stuff here. So my expected matrix, which I'm going to steal from the calculator, starts with 12.81, then 44.19, 7.19, 24.81. And those are my expected counts. So all of these are bigger than 5, or at least 5. So all expected counts which I might not want to leave this unlabeled. These are expected counts are greater than or equal to 5, check mark, and I'll just point to that table. So we're good to use a chi-square distribution, which normally we make a statement whenever we're doing this for like a normal procedure. So we can say sample is large enough to use a chi-square distribution. So I'll say use chi-square. So then the chi-square formula, I'm going to write all 4 because there's 4 of them. So it's what, 17 minus 12.81 squared over 12.81 plus 40 minus 44.19 squared over 44.19 plus 3 minus 7.19 squared over 7.19. If this were an AP exam and I were taking that, I'd want to be safe about it and show all that information as opposed to taking like a cheap shortcut and doing the first and last. Now, if we had the table from the previous problem, then yeah, I would do that because that's however many of them, 10 of them. In a previous handout, we had like 14, 2 by 7. That was a large one. So in this case, there's only 4 of them. I'm going to write them all. So 29 minus 24.81. That doesn't hurt to write 4 of them. Now, what would be bad, though, is if somewhere in the middle, you didn't write down the correct values, and they could actually knock off points for messing that up. It depends. They could be lenient about that. Now, we're supposed to get, and this is based off of what I have on my calculator, so I'm not showing that, just to save time, 4.9193. And how many degrees of freedom? Very easy to check. 2 minus 1 times 2 minus 1. 1 times 1 is 1. So I could write that too. It doesn't hurt to write the formula. 2 minus 1. 2 minus 1. In this case, it's 1. P-value, also on the calculator, 0.0266-ish, if you round to the nearest 10,000th. So that is arguably statistically significant. This is less than alpha is equal to 0.05. In this case, we reject the null hypothesis in favor of an association. And I think I just spotted a mistake. You might have already spotted that before I did and were annoyed like crazy. So I wrote there is no association twice. Null hypothesis has to be no association. So there is an association between those two variables. So I apologize for that, and I put no twice. No for the first one, yes for the second one. So there is an association for the second. So we're rejecting the notion that there's no association in favor of there being an association. So because, so I don't need to write that. So I can be kind of general. We reject. So I can also write this with an arrow pointing to that. Because of that, we reject the null hypothesis. There is enough evidence to conclude that there is an association between facial expression and self-reported pain level. And that's going to be it for this particular test and for this particular handout. So we'll go ahead and stop here.